Hello everyone. So today I have Jeffrey running here so we can check in on how he's doing. The current environment doesn't seem to be provoking any decisions, so I'm going to switch it up here just so we can get a little more action in the short time that I have to talk about Jeffery. That's the same environment. And now there is something flashing. I'll let it run its course for a bit. So in other news with Jeffery, I've been running him a lot over the course of the last few days since Wednesday, and I haven't been able to sit down and work on the errors. I might be able to do that tomorrow, but in terms of the errors, they are still occurring, and I need to isolate what type of error is occurring in each program, because there are errors that are occurring in the driver program as well as errors that are occurring in the AI in a total. Most of those are occurring in the child program of the AI, which is the AI's equivalent or the simulation of the driver program. So most of these problems and errors should be relatively related, I'm hoping. So then I can knock out a few birds with one stone when I actually find a solution to the current errors. Now, I don't think that I'll be able to make the program perfect, but I'll at least make it so that it will run without crashing, hence the crashing. So now we have a rock there, so we'll see what happens. He has been about the same amount of adventurous. That sentence was terrible. So what I mean is that Jeffrey has been exploring out into no man's land about the same amount, and the good thing about that is that the more he spends out in the area without the light, the more the AI can learn about how Jeffrey should act when his battery is low. And I have seen more of Jeffrey cheating the system a little bit. I'm not sure if the decisions are actually forcing him to do that or if it's just a coincidence. But when Jeffrey gets himself out into the dimmer light, which is the darker ring there, he begins to shoot his gun while staying in one spot outside, so that the battery bar will stay fairly low in, and it will think that he's trying to charge up, but he keeps it in a constant fluctuation between levels of charge, so that the points that he gains from just simply standing there are substantial. I don't think that this is a problem I need to fix. I think this is just the AI's randomization exploiting the game, and possibly just a complete coincidence that it occurs. I do need to make the program I was talking about on Wednesday so that I can see what the decisions are for each instinct. Now, that will be somewhat of a daunting task, considering that the instinct list is now above 200, and here we go, he's starting to explore. He's getting out into this dimmer area, and so now he's going in a straight line. And so what I noticed is that the decisions haven't been necessarily based on environment and more based on health stats, so the health bar over there and the battery bar. So this would mean that in terms of new environments, Jeffrey does not have a lot of instincts specific to those health and battery levels. So when Jeffrey has low battery, he tends to just do the same thing for every environment, because if he does not have a specific instinct in that environment already, or if he only has one instinct for one situation, then he will keep falling back on that instinct until the AI produces a new instinct for Jeffrey to enact on. So these are the new situations that I've been seeing where the battery's completely down, and so then Jeffrey will be learning a little bit more from these new situations, because the whole AI will have a chance to take this in as a sample environment, so then it can begin work on creating new instincts for this particular case of health and battery combination. So like I said, not too much excitement has happened with Jeffrey in the past couple days since Wednesday. So I think now that you've seen him run out into no man's land, there isn't really much more to show. So I will just go and run a quick commercial here while I set up the other the ball drop task, so that I can move on to the bulk of the stream, which I plan to be talking about. I know I said on Twitter I was going to be talking about refrigerators, but I changed my mind a little bit. I'm going to be talking about evaporative cooling, which is a type of refrigeration, and also touching a little bit on relativity. And so I know we talked about quantum mechanics last time, and I'm sure I butchered it a little bit, but I think that I will do a little better job of explaining at least some of the mathematical aspects of relativity. So with that being said, I will play an ad, and I will see you in a minute. Okay, I believe we're back. I'm just going to pull up a paint window here so I can get some drawings going, and then just make sure I can see what I'm doing here. Okay, so I guess I'll begin with my first topic of evaporative cooling. So that's not too complex of a topic, but it is something that not a lot of people think about. So I wanted to bring this up to you guys because I think it's a cool idea, and it's something you can try on your own, because it may be relatively useful in certain circumstances. So what I mean by evaporative cooling is basically what the name states. It's just that you can cool something by evaporating water. And so I will explain a little bit of the science behind this, but I'm just going to explain the scenario first. So there are a couple different names for evaporative cooling. Some people call it a swamp cooler, some people call it a desert cooler. This is basically just, it's something that is not very sophisticated in terms of the mechanics behind it, but in terms of the science, it is fairly practical and relatively efficient in terms of energy needed. So if you want to get as simplistic as you possibly could with evaporative cooling, then we can think of this scenario. So let's just imagine that you have a water bottle, and so there's a water bottle and it's got the cap, and so there's water in it. Obviously it's a water bottle. Now the situation I always think about, because growing up I always played soccer, so I would bring water to the game, and if you just have a small water bottle and not like an actual thermos or something, then the problem is you'd go in to play, and then when you come back out of the game, your water has been sitting there in the sun and it gets extremely hot. So the sun's just beating down on it and the water temperature goes up. And so hot water isn't the most refreshing thing once you just came back from running your butt off in a soccer game. So one way to get around this is if you have a towel or a little rag or something, you can take this rag and pour a little bit of the water on there so it gets a little wet, and so then you just wrap the rag around the water bottle, and so the rag is just encompassing the bottle. It doesn't necessarily have to be in any specific manner. It's just that you want it to be in contact with the plastic on the bottle. And what happens is the water that's on the rag evaporates, so I guess we'll just use blue. It comes off, and in the heat of the day, the sun, obviously, I live in Florida, so it's a problem that happens a lot. Well, it's not necessarily a problem, but it's something that I have a lot of experience with. The sun beating down and evaporating water. So the water evaporates off of the towel, And what happens is when water evaporates, because it has such a high specific heat, it will suck the energy out of the surrounding area in order to get it to bump up to the level where it can become steam or water vapor. It's not necessarily steam because it's not 100 degrees Celsius, but the idea is that the water can take energy from around it and use that energy to get to a higher level and change state. So to explain some of the science, and just to get my point across, when that happens, it takes the heat from the water that's in the bottle, and then so then the water in the bottle actually becomes cooler because the water on the rag is evaporating. So if you have, and this is something I've been exploring in my thermodynamics class, so if you have the enthalpy, which is H, and the temperature here, and we make a graph, then you can make this bell curve shaped graph, which is like, oh, that's terrible. So you make this graph, and it looks kind of like that. That's kind of butchering it, but so what happens is you have your temperature and you have your energy, and so let's say this is a fluid to gas graph, because we're talking about water becoming water vapor. So what happens is, let's say you start with fluid water, so HF, and it's right here. So that's where you're at. You're right here, and then you put it out in the sun, so it's on this rag, and you put it out in the sun, and the sun raises the temperature, so the temperature goes up. So then it goes up this little line here, and it gets to this temperature. So the energy has increased as the temperature's gone up. So now it's at this temperature, which is a new energy level, which we'll say is HF2. It'll be a little hard to draw, so that's HF1 and that's HF2. So then now you have a hotter temperature for your liquid water, but what happens is if you want water to become steam or water vapor, then you can't just keep increasing it. Like, the temperature doesn't just constantly increase. What happens is when it reaches the point where it can become a vapor, then you have to cross this gap of energy to reach the other state, which this side is gas. So this is liquid, and this is gas over here. And you may say, well, there isn't a specific border between those, and that's true. So what happens up in this area up here is it gets a little confusing about whether it's a liquid or a gas, and what happens is it isn't necessarily either of them. It kind of acts like both, but that's for another day. So what happens is the energy increases, and then it has to jump across this gap, so it needs a buttload more energy just to change state. And what happens is, if you actually look at a graph of the temperature of liquid as you're heating it up, once it starts boiling, it doesn't necessarily get any hotter, because what's happening is all of that energy that you're putting into it in terms of heat is actually being absorbed by the molecules, and it's being transferred into the process of converting the water into a water vapor, as opposed to just going straight into raising the temperature. So if you look at a graph of the temperature, it will actually, versus time, it'll actually go up, and then it will plateau a little bit, and then it'll go up again. Because at this point here, everything's gas. But at this point here, everything is water. And over this period of time, the substance you're working with is changing state. So it's this gap right here which is actually what we call the specific heat. So based off of the temperature it's currently at, you need more or less energy to jump to a higher, to the next state, which is why if you have water sitting out while it's fairly close to freezing, then odds are it won't jump the gap because it can't find the extra energy to turn into steam. But if you have water that's fairly close to 100 degrees Celsius, then even though it isn't 100 degrees Celsius, some of the water will still jump the gap and become steam. And this is why we have a property called water. We have a vapor pressure when you have a liquid, because what happens is you have a graph of so you have most of the molecules are built up here. So this is the number of molecules or percentage of molecules or whatever, and this is temperature. And we'll say that this is where the temperature is for a phase change of that substance. Well, most of the molecules are at that temperature, and that's why you get a average temperature that is lower than the boiling point of that substance. But if you look at this graph, and this is kind of a poorly drawn graph, but it at least shows the idea. There are some molecules that are moving fast enough and flailing around fast enough to where they can become, they can make that jump because they have enough energy, internal energy, to become a gas. So then that's why we have a little bit of a vapor pressure when you have a closed container, because some of the liquid does evaporate, even though it's not at the temperature, it's not at an average temperature where it would evaporate. But so what happens, like I was saying, is that the process of evaporating water is I believe it's endothermic. Yeah, endothermic. So it requires energy. It does not. It doesn't shoot out energy as it occurs. It's an endothermic reaction. So it means that you need to jump this gap in order to cause the reaction. And I know it's not necessarily a chemical reaction because it's a phase change, but it is a good analogy in terms. So what happens is when you have the water that reaches this point and evaporates, it will draw in the energy from the surrounding area, and the largest pool of energy would be this bottle of water that it's stuck to. So then when you come back from playing soccer, then the water that is in the bottle is now cooler, and you may think that it wouldn't be too much of a temperature change, but you would definitely be surprised. I implore you to try. Just get like a towel or even some like napkins and wrap them around your water bottle, and then while you're about to go do something, and when you come back, the towel will be drier and the water bottle will be colder. no matter what temperature water you put on the towel. So that is the idea of evaporative cooling. So I've pretty much explained everything I wanted to in that topic, and I'm not seeing any questions, so I will play an ad and transition into my second topic, which is relativity. So I will be right back. Okay, I believe we're back. So now I will be talking about relativity. And so I know that I have mentioned a little bit about this before in the quantum mechanics episode. So what I like to say about relativity is that the concept itself is harder to grasp than the math and the application. Now, in some terms of relativity, it's a little bit harder to grasp the math. When it gets into the more electromagnetism and gravitational time dilation and whatnot. But what I'm planning to talk about, which is the relativistic effects of moving at speeds close to the speed of light, I want to point out that the math itself is not too difficult to grasp, but I will do my best to explain the concept as well. So, with relativity, so I'll just explain the word relativity in general. So, let's say that you have someone moving this way. And so let's claim this is a vector. So let's say let's just make this a picture. So we'll put a car here. That is a terrible car, but we're living with it. It's a truck. Okay. So there's a car on the road here, and he's moving this way. And let's say there's an on-ramp to the highway, and I'm going to get rid of that one. So there's an on-ramp to the highway, and so I'm just going to add some details in here so you can see this is a road, and we got the on-ramp. So you see what I'm saying. So then we have another car, and let's make this one blue. It's just going to be a big truck. So we got wheels and a front. So it's kind of like a dump truck or whatever. Okay, so we have this car and he's going this way. So then they have their own speeds relative to the ground, but in terms of relativity between each other, so let's plot out the vectors. So we have the first vector, and then if we add the second vector, actually it's so in terms of normal Newtonian relativity, or classical relativity, you would have the velocity of the first car is equal to the velocity of the second car plus the velocity, the relative velocity. So that's the velocity of the first car with respect to the second car. So what this means vectorially is if we have this vector, then this vector is equal to the other car's velocity plus the relative speed. Actually, I'm going to do this in a different color so you can see it. the relative speed and the relative velocity of the first car, this car, with respect to the truck here. So this basically means that the first car is moving in this direction, with this relative velocity with respect to the other cars. So if you were videotaping the car from the truck, this is the direction you would see it in, and that's how your mind would perceive it. But in terms with the ground, the two cars are both heading in different directions from the relative directions of the cars. So the first car would see the truck moving in this direction. So for the first car, the truck is actually moving backwards and slightly to the left, or slightly up, which you can see that this portion of the vector is smaller than the car's portion. So you get this vertical portion, but then there is a subtraction of the rest of this vector, and that's why we see the relative velocity of the truck being to the left somewhat with respect to the first car. So that's regular relativity, and so that's what people will. That's not necessarily what people will normally mean when they say relativity, because I feel like there's more of a popularity with the special and general relativity, the theories by Einstein and his colleagues and others that followed him. So I'm gonna clear the page here. So what happens is that when you get closer and closer to the speed of light, things start to get a little weird, because basically the speed of light is inachievable. It's infinity in terms of velocity. The only thing that goes the speed of light are electromagnetic waves, so like light and radio waves and whatnot. So and that is what we base the maximum speed on. So when what causes something to not be able to achieve the speed of light is the relativistic effects when that object gets close to the speed of light. So if you have something going half the speed of light, so let's say 1/2 times c, which is the normal symbol for the speed of light. And for those of you that don't know, the speed of light is around approximately 3 times 10 to the 8th meters per second. And I believe that is about 180,000 miles per second. I wouldn't quote me exactly on that, but I just got distracted by the AI. Just did something a little strange to catch the ball, and that's fairly smart. Yeah, so this is the speed of light in terms of the metric system, and that's what most people will use in a physics class, although it is actually a little bit smaller than that. It's about I think I was reading 2.99994 something times 10 to the 8th. So it's fairly accurate when you're doing everyday math with the speed of light, and I'm not sure why you would be doing everyday math with the speed of light. But okay, so let's say an object, let's just make a baseball or something, is going half the speed of light. Now we'll ignore the fact that it would just tear itself to shreds on any drag it was receiving or explode. and I'm not even going to question how it accelerated to that speed, but let's say it's already going that speed. So it's going this way at half the speed of light. Now there's an equation, and actually I should explain what happens, or at least mention what happens when you get close to the speed of light. So the way that physics counters an acceleration towards the speed of light is that when an object gets closer and closer to the speed of light, it shrinks, and it also gets more massive. So it sort of gains mass in a sense. I know in most physics situations it's sort of taboo to gain mass, but this is something to do with the E equals mc squared situation. So it's not necessarily creating anything, it's just sort of trading stuff out. So what happens is it allows it to remove the extra energy that it's getting by becoming more massive. But so it becomes more massive, it shortens in the direction of travel. So if the ball is going this way, then it would become like a disc almost. It would start to shrink in that direction specifically. And then also time is dilated, and that's a strange concept for people to grasp. But basically, for the ball that's going fast compared to a bystander which is not moving in relative to the ball, or is moving at a fairly slow speed in terms of the speed of light, the ball would experience a stretched out time compared to the bystander. So for the bystander, the ball would be traveling for a much longer time than the bystander would be watching it. So let's say this ball traveled from point A to point B, and so it goes all the way from point A to point B at half the speed of light. Then the innocent bystander standing out here with a stopwatch would time the ball to get from point A to point B, and he would say that the ball took blah blah seconds to reach point B after being fired from point A at half the speed of light. But if there was a stopwatch on the ball, and we'll ignore the fact that the watch would probably break in the process, the stopwatch on the ball would read a shorter time from in getting from point A to point B than the stopwatch that was not moving. And this is due to the time dilation at relativistic speeds. So all of these effects that I've mentioned are computed based off of one equation for a coefficient called gamma. And this equation is that gamma is equal to the square root of 1 over 1, I believe it's minus v squared over c squared. And this, I'm pretty sure it's minus. So this v is the velocity that it's going, and this c is the speed of light. So you can see we have a c in our velocity, and so if we plug that in, we get a c squared and then 1/4 1/4 c squared, and so when you divide that by c squared, you just get 1/4. So this would be 1 minus 1/4, and then 1 minus 1/4 is 3/4, which is 0.75, and so we'll keep it 3/4 for simplicity's sake. And when you put that under 1, then you know how division works with fractions. So 1 over 3 over 4 is basically 4 over 3. And so then it's the square root, so it's the square root of both of these. And the square root of 4/3, I'll just do that real quick to give you an answer. Square root of 4 divided by 3 is, so for our circumstance with the 1/2 the speed of light, the gamma coefficient would be equal to 1.15, and there's some terms after this, but this is the overall number. So this 1.15 can be used to find the first the shortening of the object. So if the diameter was originally, let's say, I don't know what's the diameter of a normal baseball, maybe 8 centimeters. So if the diameter was originally 8 centimeters, and then you can multiply, so you divide that length by the gamma, which is 1.15, and at this speed, 1.15, the actual length of the ball, according to a person that is not moving, would be about 6.96 centimeters. So you can see that when you get to even half the speed of light, it is a noticeable difference in length. And so although in terms of practicality you wouldn't be able to even comprehend that difference in length based off of how fast the ball was flying past you, this length is noticeable. But one thing that you would be able to notice is that is the time dilation. So what happens is that the time that the ball actually takes we'll call t prime, is equal to the time that the ball experiences multiplied by this gamma factor. So let's say, I'm not sure how big of a gap we'll need, but we'll say that the ball would take 20 seconds to get from point A to point B. So if the ball is going at the speed of light and it takes 20 seconds, then obviously that needs to be 20 light seconds away. But that's what we measure from a non-moving reference frame. And so then the ball would experience a time of, so if we had 20 seconds and we're the one measuring it, so then we have to divide it by gamma, 1.15. The ball would only record a 17.4 second time. So then that means that this could become problematic if we ever had any space races with extremely fast spaceships. There would be some confusion with how fast the one ship crossed the line compared to the timer. Now, I'm sure we will deal with that problem when we get to it, if we ever get to it. But you can see that the relativistic effects, when you get even to the magnitude of the speed of light, they become evident in the numbers that come up. So where do we use this in actual everyday life? If you've ever used well, actually, this is a different aspect of relativity, but GPS actually has to be calibrated for the relativistic effects, because as well as moving fast, there is also relativistic effects in a gravitational field. But when you have a satellite that is far away from the Earth, then it's experiencing a different gravitational field than something that would be on the Earth's surface. So this is not that massive of gravitational field in terms of what could possibly be used for a gravitational meter stick. We could say the sun, for that matter. I don't know if you've ever seen the diagrams of how many Earths can fit in the sun, but it is a lot. I'll keep the story short. So the Earth is not that big in terms of what even our solar system has to offer, but the effects of the gravitational time dilation are evident, especially over time. So when a GPS is running for a long period of time, when a GPS company has been around for a while, then odds are that at some point in time, it's somewhat like how we have to every once in a while shift the calendar so it's why we have leap years. Relativity is not why we have leap years, but I'm trying to make an analogy. So if the Earth actually moves around the sun in about 365.24 or something days, so this is fairly close to 365.25, which means that if we just shift the calendar every 4 years, then the Earth stays fairly lined up, but it's not perfect. And so the actual, I believe that the method we use now is that every 4 years we shift the calendar, but if the year is also divisible by 100, then we don't shift the calendar. But then if the year is divisible by 400, then we do shift the calendar. So then the amount of time that the amount of days it would take for the calendar to shift one whole day without us accounting for it would be a very, very long time that will eventually become a problem, assuming that the human race continues to keep kicking it. But for now, it is not a problem. But in terms of the relativistic effects on GPS, what the point I'm trying to get across is that even a small change in the amount of time that occurs can add up over a long period of time. Now, I know I'm saying time a lot in the same sentence, and I hope I'm getting the point across, but that is the idea. So I don't have much more I want to say on this topic. Obviously, it's a little bit out of my league to try and explain more in depth the occurrence at relativistic speeds and gravitational fields, but I hope that I have at least given you some insight into the math behind relativity and the different effects that happen at very fast speeds. So I will move into my final segment, which is the segment I've been doing on my Saturday streams. So that is the segment where I pick random words and draw them. So I will play a short ad and transition into that. I will be right back. Okay, I believe we're back. So I have my paper and I have my calculator, so I'm going to just pick out 3 random words. So the first one is to, which is a horse. The second one is one, which is run. And I'm not sure if we've had that one before. And the third one is one again, which is tasty. So I'm just going to go on the fact that the horse itself is tasty. I personally have not experienced horse in as a food, and believe me, I have not experienced horse in any other way. But I would imagine that it is not the worst flavor. So if the horse were to be tasty, I would imagine it would want to run, because tasty things tend to be eaten, and a horse of all things would probably be one of the better apt animals for running away. I know cows aren't the fastest animals, and that might play into the fact that we eat them a lot. Chickens are not necessarily very large, so they can't get away, but horses, I believe, would at least put up a fight. So we're going to start by drawing a horse. Bear with me, and I know it is not a bear, it is a horse. So we're going to have the leg, and we'll get the first leg, the back, and the second leg. And they have these big muscles up here on the tops of their legs. And then the tail. Oh, the tail that doesn't shoot up into the abyss. We'll get, I'll put a little black tooth on there. Actually, no, horsetails are fairly hairy, aren't they? So give this horse a nice bushy tail. Actually, I believe horsetail hair is used in the making of violin bows because it's so coarse. It's able to create all that vibration on the string. The more you know. So I'll go back to my brown here. We got the extra leg. Don't take that the wrong way. And then the body. And then the horse head, which is going to be a little bit intricate. So we have the mouth and the ear. An interesting fact about horses, and I'm not sure why I have so many. A horse can actually see almost 360 degrees around without turning its head. So the way you can tell where a horse is looking is actually where its ears are pointing. If the ears are pointing forward, then the horse is looking forward, but you could be standing here and the horse could still see you. You would just know that it was looking at you because it would also turn its ears to face you. So horses are actually fairly creepy. So we'll give it a mane here. So we get the hair in. So I'm not sure if you guys have any other interesting facts about horses. Feel free to put those in the comments section. So now we have our horse, and this horse has been properly seasoned with a little bit of garlic. It's fairly green garlic, and we'll just add a touch of paprika in there. And now he is a baked potato skin. But so this horse is very tasty. He has been he is garnished with orange peels and other various gourmet adornments. So then there's some parsley here, and the horse, being the smart animal it is, has realized how tasty it is. And so now the horse must go fast. And if you've ever seen me draw anything, you know that fast means that a bunch of lines come out behind it. Now horses are fairly aerodynamic creatures. They have been built for speed over the years. They have strong legs and powerful necks. I'm not sure how that applies, but so this horse, with its nose and desire to eat oats, just wants to go find oats and be in peace. So it runs fast, and so we'll take out a map here. And so if you're in, let's say that Texas randomly decides that horse is the new cow, because Texas is on the leading of innovation and other aspects of society. So there's Florida. That's me. And so then let's say that the horse starts in Texas. Obviously it does not want to stay in Texas if it is going to be eaten in Texas, so it will run, and it will keep running all the way up to Canada, the bearer of safety in terms of many different aspects of history. So I'm not sure if I should if I'll be able to add that much more to this. It seemed like a very straightforward message, but I will tell you that if the horse is running, maybe you should just let that one go, because obviously it has gained the intelligence to understand that it is tasty and does not want to be eaten. And many people would argue that fairly intelligent animals should not be eaten because they are growing and evolving to a higher state on the food chain. Now, when it comes to a question of whether an animal has intelligence, that is a philosophical and psychological question, and maybe we can go into that in the future. But for now, we will just enjoy this horse that has been properly seasoned and garnished, and we will allow it to prosper and find oats in other pastures, possibly in Canada. So with that, I believe I will be signing off of the stream. I'm about to hit an hour here. So I want to thank you for watching, and if you are watching on YouTube, I just ask that if you enjoyed your time here, then maybe you want to subscribe so you can stay up to date with my antics of drawing horses running to Canada. So with that, I will say goodbye, and I will see you on Wednesday.